So now that we have an understanding of what an allowable stress is, now we can put that together into a basic design relationship to come up with shapes and geometry for the things and structures that we're trying to design. So for instance, if we have here an understanding of normal stress, we consider the sigma applied, or the stress that's applied or induced by the applied loading, and whatever that stress is, we want that to be less than or equal to whatever we are going to allow as the designer. And the same holds true for shear. We want whatever shear stress is induced or applied to be less than or equal to what we allow in shear for the material itself. And so this is the basic design relationship here. This for normal stress, this for shear stress. And here, to turn this into a design formulation, is to take this right here, this stress, and substitute our constitutive relationships, or our basic force to stress relationships here. And so this would be this N, the internal normal force, divided by the area, is this applied stress result. This is less than or equal to sigma allow, right here. And we would say that, okay, well, the area that we need for this design, A required, or this minimum from basic algebra, would be greater than or equal to N divided by sigma allow. So that would tell us what minimum area we need. And then when we design, we would choose, an area, A design, that is greater than or equal to A required. And so it's like if your required point, 48 inches squared, you're going to choose something that's half inch squared. You're not going to choose, 0.48 inches squared, because then you have to build. But basically what you design are going to be standard shapes that are available, that manufacturers use and build to make a whole structural system. And the same thing with tau applied. You're going to use this relationship here. You're going to substitute here. Let me get rid of that. This V applied, the internal shear force divided by the area that we need in shear at less than or equal to tau allow. And just in the same way, we're going to say that the area required is greater than or equal to V over tau allow. And this is going to tell us how much area we need in shear. So if we're designing a bolt and we're considering the shear failure of that bolt, it's going to tell us how much area of a bolt we need. And when we design, we can choose the appropriate diameter of the bolt. So let's, in that regard, let's take a look at a simple connection here. So I drew out a simple connection for us here. When you have a connection or any structural system, you have to consider, when you design, you have to consider how it could fail. And every way that it could fail is considered a limit state or a failure mode. If I were looking at my simple connection here, there are many ways this thing can fail, but the two we're going to focus on is, with this loading here, I could literally shear or fail, this bolt could fail in shear, and I could have any of these bars that are connected here. I could have any of these bars right here. This could yield or rupture. And so I want to examine the basic design relationship associated with each of these limit states. And for us, we're going to focus on yielding and shear in the bolt. Let's start off with yielding in the tension member. So yielding in the tension member, if I want to make a cut here, and I want to draw my free body diagram. So that free body diagram of my cut, I can choose either the left or the right, will look something like this. So here's what my free body diagram looks like, and I have my force applied here, my applied axial loading, and here I'm going to have an internal force N. And essentially in this problem here, what we're given P applied, and what we want to do is find the cross-sectional area. We want to find the cross-sectional area of the bar, or we're going to design the cross-sectional area of the bar for this limit state, so for yielding in the tension member. And to do that, we would say, okay, let me use my basic design relationship. So this would be sigma applied is less than or equal to sigma allow. And here I would have N divided by A bar required is less than or equal to whatever this sigma allow is. And typically this might be, in this case, if this were like steel, sigma allow for this material for steel would be sigma y is 250 MPa. And then again, if we want to, just like before, if we want to include a factor of safety, we might include it over here, but that's not too important here. So here, A bar required in this case would be greater than or equal to N divided by sigma allow. From basic statics, you would say that sum of the forces in the horizontal equal to 0. It would be P applied minus N equals 0, and N would be P applied. And you would plug that into there and you get A bar. And then you would choose an appropriate area of the bar. The other limit state that we want to look at is going to be here where we have bolt shear. So now I'm going to want to draw a free body diagram of either this side or a cut through my bolt, either the whole left side or the whole right side here. So here is my free body diagram for the shear failure in the bolt, essentially what we're doing here is we're given P applied, and we'd like to find or design the area of the bolt, or in some cases the diameter of the bolt. So we'll go to the diameter of the bolt, like what bolt diameter we require. We're going to draw this free body diagram, use basic statics here. So we'll say that V bolt, sum of the forces in the horizontal, is equal to 0. This V bolt represents the shear force going across the area of the bolt, and here I'd have minus V bolt plus P applied is equal to 0, and that would tell me that V bolt is equal to P applied. And then I apply now my basic design relationship for the stress induced by the shear force across the bolt area, which would be shear stress. And here this would be tau applied is less than or equal to tau allow. And whatever that number is, if it's steel, we're looking at shear yield, it would probably be about 150 MPa. Here, this tau applied is V over the area of the bolt is less than or equal to tau allow. And this would tell me, if I just rearrange this, it would say the area of the bolt must be greater than or equal to V bolt divided by tau allow. And that gives me a requirement here, and this area of the bolt could be substituted pi dB, diameter of the bolt squared, over 4, the cross-sectional area of the bolt, is greater than or equal to V bolt over tau allow. And now I could solve for the diameter of the bolt. I could solve for that diameter of the bolt. Alright, so hopefully that gave you a nice little overview on simple connections and the basic design relationship. And I will come back and maybe do another example problem with the simple connection design. See ya.